Hello. Today we will be discussing exponential functions or exponential relations, exponential increasing exponential function and decreasing exponential functions. Exponential functions are very common in physics and in other sciences. It's quite useful to learn the properties of exponential functions. Of course, exponential functions are a very large subject. We are not going to discuss all the mathematical details of exponential functions, but we will try to understand or gain a general understanding of the behavior of the exponential functions, so that we can use those mathematical relations in understanding the biological phenomena. One example we have already seen is the outbreak models, where the exponential growth is part of the model, or part of the dynamic model explaining the progress of outbreak throughout time. Okay, a very well-known common example is the water lily covering the surface of the pond. A water lily is a aquatic plant which grows on the surface of the water, still water like lakes and ponds and things like that. And when it grows, it covers the surface of the water, which is not a good thing for a pond, because then it kills all other plants and animals living underneath it. So you have to keep the amount of coverage low in order to keep an eye on it. If you're a gardener or who's taking care of the ponds, you have to keep an eye on the water lily, so it won't cover the whole surface of the pond. So one of the gardeners who is responsible for keeping the ponds clean is taking notes of the water lily coverage on the pond in the garden. If the whole pond surface is covered, the percentage is 1, or the coverage ratio is 1. And if it's 0.5, it means half of the surface is covered. So, as you can see, it takes 17 days for the water lily to cover half the surface of the pond. So the question is, how many days the gardener have before it covers the whole surface of the pond and start causing problems? If you notice the numbers, you'll see that actually they almost double every day. So this is a geometric series, an exponential growth, you see. So actually, even though it takes 17 days for the water lily to cover half of the surface of the pond, it only takes 1 day to cover the rest. As you can see, the growth rate increases every day, and the increase is faster with every passing day. You can see the graphic representation of this situation here. So this is exponential function. We know that geometric series and exponential functions are related, intimately related. So what is an exponential function? Exponential function is y equals to e to the x, or a constant times x. If the constant is 1, then it's e to the x. So, the important property of the exponential function is that its derivative is also an exponential function. As you can see, the derivative of e to the a times x is equal to a times the same function, as you can see with the equations in the red boxes. If y is e to the a times x, then derivatives is a times y. Derivative of y equals to a times y. If a is 1, derivative of y is equals to itself. Which means that the derivative, as you can see, is the slope of the curve at that point, which is represented by the blue lines there, is growing, increasing in proportional to x, and it grows similar or exactly like the function itself. So the derivative of the function is increasing in par with the function, the value of the y. If you compare it to this to simple polynomials like x squared or x cubed, we see that their derivatives also increase with x. As x increases, the derivative of these functions also increase. However, the exponential function, this increase is quite dramatic. We can see here a comparison between these three graphics. So when we look at the derivatives, we see that normally the derivatives of x cubed and x squared, they are growing linearly. However, the derivative of the exponential function grows exponentially. That's why the rate of increase for the exponential function picks up pace very, very quickly. When we try to explain the water lily example within a mathematical function, we can use a x squared function, or we can use a x cubed function. The idea is that, let's say, we know that at 35 days, the water lily coverage will be 1200 unit squares, which means that, let's say that it means that the whole pond is covered. So, to try to explain this phenomenon, if we have a x squared or x cubed function, we'll see that the growth is much more understandable or comprehensible. As you can see, even though at 35 days the whole area is covered, the difference between the 34th day and the 35th day is not that much different. So, in a sense, even though the growth picks up pace, it's still the difference between days are quite similar, or are quite small compared to an exponential function. When you go to x cubed, of course, the difference gets larger, but when you look at the exponential function, for almost 31 days, nothing happens. Then all the action happens in the last 3 to 4 days. This is the thing here is that the end point is the same for these three functions. If the water lily growth follows an exponential function, then you can understand the gardener can be fooled very easily, because almost for 30 days nothing happens, almost no growth. But then suddenly it explodes. This is very similar to the outbreak model we discussed. At the beginning of the outbreak, for many weeks, the number of cases stays very, very low, and the increase is very small. But then suddenly, within weeks, you end up with tens of thousands, or even hundreds of thousands of cases, which overwhelms the system. It's very easy to be fooled by the slow start of the exponential growth. This is not the case for x squared or x cubed or x to the 4th power type of growth. There the pace increase is much more reasonable, I should say. So let's look at the effect of these parameters in the exponential function. We said that y equals to e to a times x. And the derivative of this function is itself times a. So if a is positive, first of all, or if a is negative, what happens? If a is positive, then we see an exponential growth. But if a is negative, then we see an exponential decay. The terminology is like this. So we see an increasing function if a is positive, a decreasing function if a is negative. That's the first thing about a. The second is, to understand that the first part of this exponential growth, where nothing seems to happen, is actually, when you scale it up, you see that it's exactly the same with the rest of the function. Actually, it's picking up pace a lot. But the growth difference between each step is small. The difference between each step gets bigger and bigger and bigger constantly, because the derivative of the function is itself. So it grows, the difference grows quite fast. What is the effect of this, the absolute value of a on the function? When we look at these examples, there are three different a's, 0.25, 0.3, and 0.34. As you can see, as the a increases, the exponential function starts to pick up or grows much faster. So it's the a is kind of the parameter that determines how fast the exponential function will grow. Of course, if it's a negative a, then the absolute value of a determines how fast it decays. So the larger the absolute value of a for a negative a, the faster the decay is. As you can see here with three different negative a's, the effect on the decay of the exponential function. And also this means that the a determines the size of or the value of the derivative of exponential function. Absolute value of a is larger, the derivative is larger. So the derivative of the function for the same x is larger for a larger a, for a larger absolute value a. It's true for a positive a, it's also true for negative a. Of course, if the a is negative, the derivative will be negative, which means a decrease. It implies a decrease. If the a is positive, then it's a positive derivative, which implies an increase at that x point. So when we look at the complementary functions of exponential, which means that the function which is 1 minus e to the a times x is a complementary function. It is not, if the a is negative, the complementary function is not an exponential growth. Its derivative decreases with increasing x, and asymptotically approaches 1. So at each x, the sum of two functions, the blue and the red functions, add up to 1. For this example, the a value of a is minus 0.3. Of course, it doesn't have to be between 0 and 1. You can always multiply it with a constant. Here it's b0, it's called b0, or the constant b, which will scale up the whole graph. Of course, it will still approach in an asymptotic fashion to 0, the red function. However, it won't start from 1, it will start from b0. And of course, if you multiply the complementary function of the exponential with b0, then it will start from 0. However, it will not go to 1, but the blue function will go to b0. So this is a second parameter for the exponential functions, like a. b0 is also affects the shape of the function. Okay, let's go back to the water lily analogy or water lily example. If we try to explain the growth of water lily with the x square or x cube or exponential function, which means that you have to get to a certain amount of coverage at a certain day to explain it. For example, in 35 days, the whole area will be covered. Let's assume that either red or blue function can fit the data, the daily growth of the water lily. It doesn't mean that it's not an exponential function, because it's not an exponential growth. Because if you choose the b value, b0 value, and the a value correctly, you can approximate the x square or x cube function with an exponential function. However, for this, you can only approximate it only for this 35 days. After that, if the growth can continue, in this example, it won't continue because the whole area is covered. However, if there is still, assume that there is still enough space on the water surface to cover. So after that 35 days, still the exponential growth will pick up pace much faster than the x square or the x cube. So they will diverge dramatically after that point. So you have to understand that for certain periods of time, an exponential growth can be approximated by an x cube or an x square function. But it does not always mean that it's an x square or x cube function. After that period, you observe, if the function is itself exponential, then it will pick up pace much faster than any x square or x cube function can explain. Be careful about this. There are two important points we have to understand. First of all, the exponential function is not always e to the x. B to the x is also, b is any number. E, as you know, is a specific number. It's 2.7182, something like that. B to the x, any b, any number, power of x, is also an exponential function. However, the derivative of this equals to the function itself, b to the x, times ln b. So the derivative of any exponential function is itself times its logarithm of its base. Of course, if the b is equals to e, then the derivative of the function is equal to itself. The constant term goes to 1. So this is, so in a case, e to the x is the simplest exponential function. Exponential functions also, as we've seen in the previous video, allows us the definition of very useful concepts like doubling time, and also for the decreasing exponential functions, half-life, which it means that for half-life, when you look at the graph below, going from 1 to 0.5, as shown by the blue arrows, you have for the y value to decrease from 1 to 0.5, you have to go 2.3 units to the right on the x-axis. However, if you go to another point, another y value, 0.22 for example, and to go half of that value, 0.11 for example, shown by the red arrows, you again have to go 2.3 units to the right from that point. which is here you go from 5 to 7.3. Again, if you go to any point on the y-axis and to half that value, you have to go for this function 2.3 units to the right. This is called the half-life for this particular function. It depends on a, of course, as you have seen, the a value, e to the a times x. A determines this half-life. But as a is constant for a given function, the half-life is also constant. For this function, it's 2.3 units. So, for example, it's the same with the doubling time. We've seen the example in the outbreak models, the doubling time. So the doubling time means the time it's required for this number of patients to be doubled. And it's a constant, because if you have 10,000 patients, to go to 20,000, it takes the same amount of time to go from 10 to 20 patients. Here it's the same thing. If you want to half the value of the x, of the y, the amount of shift on the x-axis is always the same. So these are two important concepts we have to know about exponential functions, and this general view is not comprehensive in any ways, but it gives us a adequate understanding of the behavior of exponential functions, so we can use it properly to understand the biological and natural phenomena like the outbreaks using this mathematical concept. See you in the next video.